Okay, now what we have to look at is something we've already talked about a bit, which is formulas, and really naming these formulas. So, again, where we start is with our basic knowledge of formulas, of binary compounds, where we have ionic compounds, where we have metals bonded to nonmetals. We can predict, again, the charge or the oxidation number on our nonmetals based upon their placement in the periodic table. Same thing with a lot of our metals, alkali earth metals. Again, we can do a similar thing with our transition metals, but it's not always the easiest because they have this big D block, so sometimes they just lose their s orbital electrons. Sometimes they lose some d electrons as well. So it's a little bit more, there's more of a process in it. But let's look at some basic ionic binary compounds. So calcium, we know, is +2. That's our cation, our positive ion. And we know it's +2 because of its placement in the second row in the periodic table. Chlorine is a -1. We put them together so that their charges are going to be balanced. So if calcium needs to lose 2 electrons and chlorine needs to gain 1, well, then we need 2 chlorines for every 1 calcium. Now, the name of this compound, the first part stays the same. Calcium is calcium. Chlorine, however, gets an IDE ending. So it becomes chloride, IDE. Next one, similar. We have barium. Barium, again, is an alkali earth metal, just like calcium. Oxygen is 2 away from a noble gas, so it's going to gain 2 electrons. And we have barium oxide. Notice on this one, we don't just cross their charges because we don't need to. We don't need 2 of each because this is losing 2, this is gaining 2, so they can just go together. And again, remember with ionic compounds that they're forming lattices, so this is only the smallest formula unit or smallest repeating unit. One more example here, potassium and sulfur become potassium sulfide. Notice all these single element ions have an IDE ending. So all the ones on this, if it's a single element ion, it's an ion derived from a single element. Doesn't matter if there's multiples of them, as long as it's derived from a single element, then it's going to have an IDE ending. So our next one, this is where things get a little bit different. Notice this is iron with a +3, bromium with a -1, so it'd be iron, bromide. That part is easy. One thing we have to recognize, though, is with our transition metals, they can have multiple oxidation states, just like we saw in this. You'll notice that iron has 2 major oxidation states, a +2 or a +3, and so iron we have to state its oxidation number in the formula. So we're going to have Roman numerals in the middle of the formula saying iron 3. Now, it's not saying there's 3 irons because there's not. It's referring to the oxidation state or the charge on the iron. And really, we shouldn't use those terms at the same time because they're not really charged once they're in the complex. It's more of their oxidation state. So now we put these together. We have another one. Chromium is a transition metal. So it's chromium 3, we cross the charges, and we get oxide. So that is our binary ionic naming. And if you like rules of how to follow, we can follow these rules. You write down the chemical symbols, you write down the oxidation numbers that you pick off the periodic table above them, you cross those to the bottom, you remove the positive and negative signs, so we cannot have the charges once we're writing a chemical compound, and you remove any ones or duplicate numbers, or if they're proportional, you're going to have to reduce those as well. So here's this nice little list of some of the very common ions that we're going to run into. Notice a lot of alkali earth metals and stuff that are +1 ions. Hydrogen's a +1 ion. Some alkali metals, alkali earth metals in this, and also some transition metals, aluminum or aluminum right here, and then our anions down on the bottom. Again, these are our common anions that we might run into, and notice they all have that IDE ending. Notice one that you might be kind of surprised to see there is hydride, but if it's bonded to an alkali metal, again, hydrogen's normally going to be +1, but if it's bonded to, say, lithium, which also wants to be a +1, well, lithium loses its electron easier than hydrogen does, so we could potentially have a lithium hydride. That is a potential compound for us. Now we're going to throw in some of those polyatomic ions that we've talked about before. And our polyatomic ions, remember, are covalently bound groups of elements that overall have a charge. So when we put these together, we're going to really follow the same rules. Here we have lead. Lead is +2 in this case. PO4 has a -3, so our charges don't bounce them. We cross them. Notice, if we need to take two of our phosphates, we need to put it inside parentheses. So if I need to take multiples of that phosphate, I have to put it inside parentheses. Now notice why we're doing this again, is if we take two phosphates, we have two -3 charges for an overall gain of -6, or gaining 6 electrons overall. If we have this 3 here, well, 3 times 2 is a +6, so it's losing 6 electrons. So that's how those ratios can come together to form a bond, again, is if the positive and the negative charges are going to be equal within the compound. So we have to have an overall neutral compound when we draw these. Now that we have a more complex compound, let's look at what's actually in this. So what this is stating, the subscripts are stating that's how many of those individual elements are in the compound. So the 3 after the lead are saying that in this compound there's 3 leads. The 2 again applies all the way across that polyatomic ion, all the way across everything in the parentheses. So it applies for the phosphorus. There's 2 phosphorus, but it also applies to the oxygen. And since there's already 4 oxygen, there's 2 groups of 4 oxygen. So there's a total of 8 oxygen atoms in this compound. The name of it would be lead 2, in parentheses, phosphate. Now, notice this is very similar to our names before. So we could previously have had an ion like this, P-3. That would have been phosphide. But now what we have is a polyatomic ion that's named phosphate. So anytime you see an ATE ending, you have to be aware that that's most likely going to be a polyatomic ion. Now, the number of oxygens that are attached and the overall charge, that part's not as easy, and that's where it kind of comes down to memorization. But some things that we can know just from the names is that IDE endings are going to be single element ions, ATE endings are going to be polyatomic ions. Now, you might not like seeing lead with a 2 there, because lead is actually in a group, it's in the carbon group, but because it's to the left of the zigzag line, it has a D block electron, so it's going to behave as a transition metal, so it can have multiple oxidation states. Whoa, now we just get a whole bunch of examples to look at. Okay, so here's calcium with nitrate. Remember, we could have had N-3 is nitride, but NO3 with a -1 charge is nitrate. Now you'll notice we had PO4 -3 was phosphate. Now NO3 -1 is nitrate. So again, the difference is due to the oxidation numbers and of the element it's based upon, but really how we know what these are is it comes down to memorization. We have to remember what a phosphate is, and we'll have to remember what a sulfate is, and we'll have to remember what a nitrate ion is, because these are very, very common polyatomic ions. Now though, let's look at how their charges are crossed. Notice we have a +2, -1, so we cross those charges, we get CaNO3 with a 2 outside of that parentheses. Again, what that means in this compound is there's 1 calcium, there's 2 nitrogens, and there's 6 oxygens, just like that. And the name is just the 2 parts together, calcium nitrate. That is its name. Heading down to the next one, now we have aluminum. Aluminum, we know it's charged from its placement on the periodic table. Hydroxide, OH-1, is another polyatomic ion. Now notice it doesn't have the ATE ending that we would like, but notice its name is just what's in it. Hydro from hydrogen, and oxide from the oxygen that are together. So if we're putting these together, again, if we need multiples of that hydroxide, we're going to have to put it in parentheses with that 3 outside. So that is telling us, again, there's 1 aluminum, there's 3 oxygens, and there's 3 hydrogens in that structure, and it is called aluminum hydroxide. In our next example, we have barium. Again, we know it's charged from its placement on the periodic table. Sulfate is one of the polyatomic ions we have to remember. Notice crossing their charges is 2 and 2. So we don't need to put the 2's. We would reduce those subscripts if it came out to that. Or we can just put them together. Barium sulfate. Notice no parentheses now are needed if we're not taking multiples of that polyatomic ion. With sodium and phosphate, notice phosphate has the -3, sodium with the +1. We can put these together. And again, only use parentheses when we need multiples of a polyatomic ion. Just because we're using parentheses now, don't mean we need to put parentheses around the sodium. That would be incorrect. We do not want to do that, only if we're taking multiples of a polyatomic ion. Last one we get out, and this is a good one to look at. We have potassium and sulfate. We'll put them together. We need 2 potassiums for each sulfate. Now, some people get excited and they see a 2 and the 4, and they want to start reducing those, but sulfate is SO4. We can't change the SO4. We could only reduce the numbers if there was a number outside in parentheses. Outside of the parentheses, I'm sorry. So here's a little list of rules for naming our ionic compounds. So if we have a binary compound, so that's just our two elements, that means it takes monatomic ions. We can find the charges off the periodic table. We put the cation first, the anion second, and the anion is always changed to IDE. That's pretty easy. I think binary ionic compounds are pretty easy. For our tertiary, that means they have to contain at least one polyatomic ion. So we have to find that polyatomic ion, recognize it, and name it. The cation still is going to go first. Now, there is a few polyatomic cations, but not very many. The vast majority of our polyatomic ions are actually going to be negative anions. So now what we're going to have is most are going to have an IT, ATA, or AT ending, and there's a few IDE. But we don't change their names, we just use the names that they have. Now here's a pretty full list of polyatomic ions. I'm not going to make you memorize all of these because it's really not necessary, and some of them we're not going to have a lot of exposure to in general science, general chemistry here. But some of these are going to be very important, and there's a few on here that I will give you on a list to memorize. And just so you know that this also is just common polyatomic ions. So this is not an exhaustive list of all the polyatomic ions that are there by any means. What we're going to do next, though, is we're going to focus over here on molecular compounds. So these are binary compounds that are made out of just nonmetals. And what we need to do is use a completely different naming system because there are no charges, there's no transfer of charges. Now we're going to name these molecular compounds, again, only if there's nonmetals present, based on just a simple numbering system. So for these, again, they have to be a nonmetal bonded to a nonmetal to have a covalent bond or have a molecular compound. So the first element is named first, the second element is named second. We do still end these in IDE, notice. And then we add prefixes to say how many there are, because again, they don't have charges or predicted charges that we can get from the periodic table, so we have to say what there is. So down on the bottom here we have some examples. We'll just move it up to the top. So the first one, we have N2O. Again, those are both nonmetals, so we know we need to use our molecular naming system. Because there's two nitrogens, we say di. Di is our prefix for two, dinitrogen, monoxide. So the monoxide is telling us there's one. Now if we have one of each, this is just nitrogen monoxide. Notice we don't use mono on the first place. If there's one in the first position, it's just assumed that there's one. So we only start using numbers on the first element if it's more than one. But we do say it on the second. Next one is nitrogen dioxide, because there's two oxides. Next one, we have dinitrogen, two nitrogens, and trioxide, three oxygens. Dinitrogen tetra, tetra for 4, and dinitrogen pent, pent for 5. Again, if we go back for a second, we can see our numbering: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And we could go beyond that into 11 and 12, but, you know, even deca, nona, that's not going to occur most of the time. Most of our compounds are going to be maybe hexa or less for our molecular compounds. Here's just a few more examples. This one we've already had, but CO, just carbon and oxygen, it's carbon monoxide. Now that's one people probably already knew, but didn't know why it was named the way it is necessarily. So CO2 then is carbon dioxide because of the two oxygens. SF6 is sulfur hexafluoride. Notice again that the anions are still named as, just like we name ionic anions, the IDE ending. Now here we have triphosphorus hexabromide. Again, they both have to be nonmetals to use this naming system. Okay, so I said I'd give you a list of common polyatomic ions that you really need to know, and here is how many are on this list. Well, there's 10 negative, 11 total polyatomic ions, but these are really the most common of our common polyatomic ions. Notice we have acetate, bicarbonate, which really we should probably start calling hydrogen carbonate. Bicarbonate is kind of the old name. And notice what hydrogen carbonate is. It's just a hydrogen bonded to a carbonate ion. We have hydroxide that we already looked at. Hypochlorite is an important one that we haven't talked about yet. Nitrate, you've already seen. Nitrite. Now notice there's a difference between nitrate, NO3 minus 1, and nitrite. Anytime we have a nitrate or a nitrite, the ITE always has one less oxygen. And again, both of those are different than our nitride with an IDE ending. So we can have ATE endings, ITE. Both of those are going to be polyatomic ions. IDE is just that single element ion again. So the other one we'll see on here now next is phosphate. Notice phosphate, we already looked at, is PO4 minus 3. That's phosphate. There is also a phosphite that's not on this list, which would have one less oxygen. And again, just like we've said before, those would both be different than phosphide with an IDE ending. Notice below that we have our sulfate and our sulfite. Again, those are following that same rule of one less oxygen for the sulfite as opposed to the sulfate, and then a good positive polyatomic ion that we're going to see a lot, ammonium. Now, the reason I'm showing you this is we need to know our polyatomic ions if we want to name our acids. So we're going to look at acid naming now. So we had ionic naming, binary ionic naming, binary molecular naming, naming ionic naming with polyatomic ions, and now we're going to have naming of acids. So if we have simple acids, say HCl, what we're just going to say is basically what's there. So this is going to be hydro. So hydro because there's hydrogens attached. And then it's going to be based on what the ion is that it's attached to. Chlor, and then ic, acid. So if it's an acid based on a single element ion, it's going to have a hydro beginning and an ic acid ending, hydrochloric acid. Now, how do you know they're acids? Well, they're acids because they have only hydrogen ions in the cation position. So this is hydrochloric. Now, another example, HBr, hydro again, and we have bromic acid. So again, same beginning, hydro, same ic acid. Bromo is just what it's attached to. So I could even get rid of the bromine piece, put a different element there, say maybe hydro sulfuric acid. So this is hydrosulfuric acid because it's just hydrogen bonded to a single element ion. But now here's where things can get a little bit tricky. This is hydrosulfuric acid, right? H2S. But we could also have hydrogens bonded to this sulfate polyatomic ion. We could have H2SO4. Now this is not hydrosulfuric acid. If we have a sulfate in 8-ending acid, that is going to become just an ic acid. So this is sulfuric acid. So we had hydrosulfuric, which was this. This is just sulfuric acid. Now if we change some things, I'm going to erase that bit and erase this. And if we change this to sulfite, SO3, then it's no longer a sulfate, obviously. It becomes a sulfite, and sulfites, we have to change this as well, become OUS acids. So we have sulfurous acid. So we had hydrosulfuric, sulfuric. Now, a few more examples of our acid naming. Again, we've already had hydrochloric. Again, it's hydro and ic because it's based off of just chlorine. Sulfuric acid is hydrogen attached to a sulfate. So the 8s, again, become ic acids. Same thing for nitric acid. Nitric acid right here. Again, that's based on nitrate, ATE. If it was nitrous acid, it would be on our NO2, right? NO2 minus 1 is nitrite, so it would become nitrous acid. Sorry, it's kind of difficult to keep them track in your head. Perchloric acid. This is a perchlorate polyatomic ion. It was on one of those lists that I showed you earlier on. Phosphoric acid based on phosphate, again, with that ic acid, and acetic acid based on the acetate ion. Now, they write it a little bit differently, but our acetate ion is C2H3O minus 2. That's the same thing as this. It's just written in a different order with that hydrogen attached. Attach a hydrogen to acetate, we have acetic acid.